Hi, and welcome to 7.2 Centripetal Acceleration and Force. In this lesson, students will be able to calculate the centripetal acceleration acting on an object undergoing uniform circular motion, as well as the centripetal force. So, uniform circular motion, we learned in the last lesson, is when an object that moves in a circular path moves in that path at a constant speed. Here's a question. Is the velocity of an object undergoing uniform circular motion constant? We already kind of mentioned it. Yes, it's a constant speed, but the velocity is not constant. Why isn't the velocity constant? Because the direction is changing, and velocity is a vector. And vectors have magnitude and direction. Both things describe that vector quantity. So since the direction is changing, the velocity is changing. That vector is changing. So if there is a change in velocity, the object must be, what do you think? Changing velocity sounds familiar? The second equation on the back of the reference table, if you have a change in velocity over time, you are accelerating. So today we're going to talk about centripetal acceleration. All right, so what direction is the object accelerating? First of all, acceleration is a vector, right? So we have to figure out, well, if it's a vector, it must have a direction associated with it. And since this thing is constantly moving all around, where's the direction of the acceleration? Let's see. Okay, so at this point, the velocity vector is pointing this way. And at the very next instant, where is the velocity vector going to change to? Like, where is it going to point next? It then points in this direction here. Oh, well, this direction here. Boom. Okay, so what direction did it end up moving? The velocity vector is moving this way, and then it moves again, and it's moving this way here. Okay, these two tiny directions should show you the direction of the acceleration. It's always moving towards the center of the circle. It wants to try to get towards the center of the circle, but it's not getting there. Why isn't it getting there? It has tangential velocity pointing this way. So it's already moving this direction, but it's trying to move towards the center. Centripetal acceleration. An object moving in uniform circular motion undergoes a change in velocity. Therefore, that object is accelerating. This acceleration always acts towards the center of the circle, just like that. All right, so if we're moving clockwise in this direction here, or even counterclockwise, the acceleration is still pointing this way. But since it's moving clockwise, that's why the velocity vector is there. All right, so you might be asking yourself, okay, cool, so are we going to use the same equation for the centripetal acceleration? And the answer is no. All right, oh, you can see it points always towards the center. All right, the equation looks like this. All right, we could derive it, but we won't. So this is the velocity being squared, and you divide it by the radius of the circle. So the size of the circle does have to do with what that centripetal acceleration is going to be. Okay, so that's our equation. Beautiful. So you might be wondering, why is it called centripetal or centripetal? It comes from Latin. It has Latin origins. Centrum for center, and petere for seek or to seek. So centripetus is center seeking. So centripetal, center seeking. It's always pointing towards the middle of the circle. That's important. Like, this is going to be a really good multiple choice type question. They're going to be like, what direction is the acceleration pointing? And they'll have all these different options. The center seeking, centripetal, always center seeking. Now, you might have remembered from the objectives, we're also going to do centripetal force. So what direction do you think centripetal force is going to point? Or better yet, since it's accelerating, think of Newton's second law. The net force is equal to the mass times the acceleration. These are both vector quantities, and we accelerated in the direction of our net force, didn't we? So yes, centripetal acceleration, centripetal force. They point towards the center of the circle, the centripetal force as well. It says the centripetal force is the net force that keeps an object moving in uniform circular motion. This force always acts towards the center of the circle, just like the acceleration does, because it's still an example of Newton's second law, where the net force is equal to ma, and a in this case is equal to v squared over r. So don't forget, you could say m times v squared over r. This is for the acceleration. So you could also write the equation like that. Where are these equations in your reference table? We kind of mentioned it in the last lesson. They're on the back page, right over here. All right, so this looks very close to Newton's second law. It's just for centripetal stuff. And this is acceleration, centripetal acceleration. And you could see they have the two different ones in case you forget what the subscript in the C is, as well as over here, there's the centripetal force. Now, you might want to write in the other version of this. So instead of ma, it's mv squared over r, because a is equal to v squared over r. So if you want, helpful tip, write it in. All right, so let's talk about centripetal force. I'll stop saying it like that, centripetal force. What kinds of forces can act as a centripetal force? Am I introducing a new force like friction? We introduced there's a frictional force. And gravity, we introduced there's a gravitational force. Is this a different thing? Is it its own thing? Or can you have different types of forces that act as a centripetal force, that cause the thing to move in a circle? So what are some forces that you can use to make a thing move in a circle? What do you think? Think about it. Critical thinking. All right, let's answer that question on the next slide. All right, centripetal force is actually an umbrella term. It's not a new force, like how there was a new force, there's a frictional force. There's a new force, there's a gravitational force. Okay, it's not a new force, it's an umbrella term. A lot of different types of forces can act as a centripetal force, as long as it's pulling something in a circle. So over here, we have a classic physics demonstration that I like to do in the classroom. You have a piece of string that's attached to a bucket or a cup that's filled with water, and you swing the filled cup around in a circle, in a vertical circle. Classic physics demonstration there. What is the force that is acting as the centripetal force? You might say, oh, well, the centripetal force is definitely pointing this way, right? But what is the force that is causing that? What is acting as the centripetal force? Pause the video, think about it. Tension. Tension in the string is acting as the centripetal force in this case. Okay? So tension a lot of times is going to be a good example of a centripetal force. Ooh, this one's a tricky one. So cars turning in a circle. What enables the car to make a turn? How does the car drive in a circle? All right, or around a turn with a certain radius? What is the force that acts as the centripetal force? Pause the video and think about it. The answer is the friction between the tires in a road. Another way to think of this is picture a really slippery road. Maybe it's very icy. Picture there's no friction between the tires in the road at all. Would the car be able to turn in a circle? No, you need the friction between the tires and the road in order to turn in the circle. So in this case, friction acts as the centripetal force. And you could probably guess, wow, we know an equation for friction, and we even know that the centripetal force is equal to the mass times the centripetal acceleration now, or mv squared over r. Wow, we could have a lot of fun with those equations. Cool. All right, so this is showing Earth with its natural satellite, the moon. I don't know why they colored the moon in red in this situation, but the moon does move in a circle around the Earth. Is there a rope that's tethering the moon to the Earth? No. What is the force that acts as the centripetal force in this case? Pause the video and think about it. You probably guessed it's gravity. And hey, we know that Fg is equal to Gm1 m2 over r squared. And we also know that the centripetal force is equal to mv squared over r. Wow, so that's like some really cool fun that we could have when talking about centripetal force and gravity, when gravity acts as that centripetal force. All right, I got one more, and it's a tricky one. Have you ever been on Starship 3000 before? There's one in Playland in Rye, New York. It spins you around. Maybe this picture will ring a bell. All right, that's the one that spins you around and it pushes you up against the side and you kind of get stuck there against the side of the wall. You're moving in a circle. That thing is spinning in a circle. What is the force that keeps the riders moving in a circle? Pause the video and think about this one. All right, you ready for the answer? The force that acts as the centripetal force in this case is the normal force. The normal force acts perpendicular to the surface. All right, so it's pointing this way. All right, so yeah, that's a really cool example of a centripetal force where the normal force is pulling them inwards. Imagine the wall vanishes. They would all go flying with their tangential velocity, but they don't go flying in their tangential velocity because the wall is moving in a circle towards them and the wall pushes on them with the normal force. Very interesting stuff. Remember, the centripetal force is the net force that keeps the object moving in uniform circular motion. This force always acts towards the center of the circle. Again, a very good multiple choice question. So, example one, a 2,000 kilogram car moving at a constant speed of 25 meters per second takes a turn around a circle with a radius of 200 meters. What is the centripetal acceleration of the car? The centripetal force, the net force, the frictional force, and the coefficient of friction between the tires and the road. Seems like a lot of questions, but maybe it's not as many as we think it is. Let's see. All right, so some given information. And you're looking for the centripetal acceleration in part A. So we use the formula for centripetal acceleration. AC is equal to V squared over R. Now don't forget, you also have this one, all right, equals MAC. The reason I knew to get to this one is because I looked at what the given information was. So sometimes we'll trick you and be like, oh, we'll give you the force and the mass, and you'll have to use that to find the acceleration. Just so you know. All right, so then you plug in. And you get 3.125. What are the units? Oh, we didn't talk about this. What are the units for centripetal acceleration? Still just the units for acceleration, so that's convenient. I'll leave it as a long decimal because we're going to use this number in the next part. And part B says, what is the centripetal force? So now we could use that version of Newton's second law. Fc is equal to MAC, F equals MA, still holds true. We're just moving in a circle now, and this will tell us the net force that's acting as the centripetal force. All right, so this is going to be 3.125, and you get a centripetal force of 6,250 newtons. That's causing the car to move in the circle at this speed. All right. Then it says, what is the net force acting on the car? Well, the definition of the centripetal force is that it is the net force. Part C, the net force is equal to the centripetal force. So we could just say the net force is equal to 6250 newtons. And then part D, very similarly, see, I told you there's not many questions here, says what is the frictional force? Well, the centripetal force in this case is the frictional force. So the frictional force is again 6250. So these two questions are just basically asking, do you know the definition of centripetal force? Centripetal force is the net force that's acting on the car, and in this case, the frictional force is the thing that's providing that net centripetal force. So part E says, it's kind of leading you into, now that we know what the frictional force is, it leads you into being able to do part E. If part C and D weren't there, it might be a bit of a curveball. If you just had the centripetal force and then all of a sudden part E is like, what is the coefficient of friction between the tires in the road? You'd have to make the jump from, oh, I remember the centripetal force is the frictional force. No work necessary there. So part E, this is the fun equation. And this is 6250. We're looking for the coefficient. The normal force, ooh, we don't know what the normal force is. It's 2,000 kilograms times negative 9.8 meters per second squared, or just really the magnitude is fine. So the coefficient is equal to that 6250 Newton divided by the weight. I just wanted to show you the weight is 19,600 newtons in case anybody found FG separately, and that's equal to 0.33188. We'll call it 0.32. That's the coefficient of friction between the tires and the road. Now again, I kind of snuck in, we've done so many where the normal force is equal to the weight. I could draw a free body diagram and show the net force equation, but I'll just put it right there. Okay, if you wanted to, you could even draw in the frictional force acting this way. That's the direction of the frictional force. If you were like looking at a head-on image of the car, like these are the tail lights, and the car's coming towards you or away from you, but it's moving in a circle this way. Or like, it's hard to draw, away from you or towards you. Anyway. All right, example 2. Should look very familiar. It's the same situation as the last lesson, but I wanted to calculate the acceleration and the tension in the string. Okay, so it says a 1 kilogram rubber stopper attached to one end of a string. A student rolls the stopper overhead in a horizontal circle with a radius of 0.75 meters. The stopper completes 12 revolutions in 6 seconds. What is the acceleration of the stopper? And the tension in the string points this way. All right, so what is that? We're really looking for the centripetal force. So that's a tricky way to ask that, I guess. They could have just said, what is the centripetal force? So you had to know that in this case, the tension in the string is acting as the centripetal force, so I better calculate that centripetal force. But it would be helpful to know what the acceleration is first, the centripetal acceleration. So let's start by writing our given information on the side. So it says 12 revolutions in 6 seconds, so I'm going to use the letter N for the number of revolutions. So you could even do 12 revs like that, okay? All right, so we want to be able to say what is the acceleration. We want to be able to use AC is equal to V squared over R. Well, we don't know what the velocity is, but we could find the tangential velocity. V is equal to 2 pi R over the period. And we also don't know what the period is, so we have to calculate the period. The period is equal to the time divided by the number of revolutions that it completes in that amount of time. So in this case, 6 seconds divided by 12 revolutions is 0.5 seconds per revolution. That's the period of time. This is the same as yesterday. And then the velocity is equal to 9.4 meters per second. Okay, now we know the velocity, so we can calculate the acceleration. So this is the new thing for today. AC is equal to V squared divided by the radius, 0.75. So the centripetal acceleration is 118.4 meters per second squared. Cool. I wonder what would happen if the radius is longer or shorter. How would that affect the centripetal acceleration, and how would that affect the velocity? Interesting. I wonder if we'll do a lab where we explore how those variables affect the centripetal acceleration, velocity, and the force. So let's calculate the force, the centripetal force, which is being supplied by the tension. Now that we know the mass and the acceleration, we could use Newton's second law to calculate the net force, or the centripetal force. So Fc is equal to m times ac. We're looking for the centripetal force because in this case that's equal to the tension. This is 1 kilogram times the answer that we just got. So since it's 1 kilogram, kind of boring. It's the same force, but what's different about it? What's going to be different over here? What are the units for centripetal force? What are the units for tension? What are the units for any type of force? A Newton. Okay. And then again, if we change the acceleration by changing the radius, how would that affect the force? So in effect, like, how does changing the radius affect the force? Think about that, and in the lab that we'll do for this, we will explore how the radius affects the force, among other variables. Okay, one more thing I wanted to talk about with centripetal force is the idea of a centrifugal force. You might have heard of centrifugal before taking this class, and I'm talking about centripetal. So are those two things the same? No, they are not. So in this slide, I tried to describe the difference. All right, so centripetal force is the center-seeking force that keeps the object moving in a circle. All right, that's what we're calculating. Centrifugal force isn't really a force. It's a fictitious force that's felt due to an object's inertia as it moves in a circle. So it's not like you're exerting a centrifugal force on something. It's because of the object's inertia. It seems like there is a force, and it seems like there's a force that's pointing in the opposite direction than the centripetal force. So this is leading to some misconceptions about centripetal force. Centripetal is always center-seeking, but in real-life experiences, like maybe you're turning in a car, you might feel like you're being pushed to the outside of the circle. All right, so I have like a little animation that describes this. Now, this is very abstract. It's like a theoretical. If you had this silver platform here and a tennis ball sitting on top of the silver platform and a centripetal force that's pulling it in towards the center, all right, this platform is going to move. It says the ball's inertia keeps it moving in a straight line unless a centripetal force is present. So right now, let's negate friction. There's no friction here. All right, but the platform is attached to a centripetal force of some kind. The ball isn't. So the platform will rotate, but the ball, because of its inertia, continues moving in a straight line. Let's see that one more time. Again, this is a very weird, abstract example, but it is applicable to real-life scenarios. So the point of this is that the ball's inertia wants it to keep moving in a straight line. Well, how do you get the ball to move with the platform? You need to exert some kind of centripetal force on the ball. So let's put a wall next to the ball. So this is a little piece of wood, and the ball is in contact with the wood here, and it's kind of like the Starship 3000 example, where the wood supplies a normal force. These two things are being squeezed together, and the normal force is going to get the ball to move in that circular path. So it looks like this. Boom. Now that the wall is there, it's exerting the centripetal force. I'll color it with blue. All right, so there's a centripetal force pulling it in towards the center. But what does the ball, if you were the ball, what would it feel like? It says the wall provides a centripetal force in the form of a normal force. Centrifugal force, let me use red now. Centrifugal force is felt by the ball because the ball wants to go straight. So since the ball's like, I have inertia, I want to go this way, but the wall is like, no, you don't. You're coming in towards the center of the circle. The ball feels like it's going to be squeezed against the surface, and it's being squeezed against the surface this way. So this is the direction of this fictitious centrifugal force that only arises because of the ball's inertia. It wants to keep going this way, but the wall at all points is saying, nope, come in towards the center of the circle. So now that we know that, let's watch it one more time. And it says the centrifugal force is felt by the ball because it wants to go straight. It is squeezed into the wall. This makes it seem like there is a force pulling the ball away from the center of the circle. Now you might be saying to yourself, Mr. Nangle, this is a very weird situation. Why is there this floating platform with a piece of wood and a tennis ball? You've experienced this before. So in a real world example, it would look like this. We have our red convertible here, and we are a green person inside the red convertible who has phasing capabilities. We're like one of those superheroes who could phase through walls. So we're not going to feel this centripetal force that's causing the car to move in a circle. We're going to phase right through it because of our inertia. Our inertia keeps us moving in that same direction that we would go through. If the car wasn't there, that's the direction that we would go. But, we're not superheroes with that capability. So when the car turns, we are buckled into the car and we turn with the car, much to the chagrin of our inertia. Our inertia wants us to keep going this way. And what happens is as you make the turn, your inertia is saying, no, I want to go against what you're trying to make me do, right? Yeah, that's basically what it is. So it looks like this. And you feel like you're being pulled towards the outside, but that's only because your inertia wants you to keep going this way. In reality, you're not being pulled. There's not an invisible force pulling you to the outside, but there is a frictional force between the cars and the tires that are pulling you here. And since there's a frictional force between your butt and the seat, so that's also, and then hopefully you're buckled in and you're all attached pretty much to the car, but you feel your body wanting to go this way. And if you look at anything in the car, if there's something dangling from your rear view mirror, something like that, then it goes where the inertia wants it to go. You could see it going to the outside. And if you put yourself into like a frame of reference of the car, it looks like there's an imaginary force that's causing these things to move around in the car. But in reality, it's just the inertia, which is not a force, right? So centrifugal force just arises because of the object's inertia, and it's important to make that difference between centripetal force, which is the thing pulling you in towards the center of the circle. It's always towards the center. And that's about it. Thanks for watching and have a great day.